Okay, so inertia in and of itself means that we will keep moving unless an outside force acts upon us, but we have something called this moment of inertia, which resists this rotation at the beginning of our motion. This is our equation for moment of inertia. It's represented just by an I, okay, a capital I. And its equation is I equals m times r squared. So the m value means mass, r value means radius, okay? Moment of inertia has some different equations based on the shape of an object about how its mass is distributed around this center or this axis point. And I'll show you those different equations as we go through, but what it's just saying here, this sentence is in your book kind of describing what the equation tells you. Okay, so moment of inertia is a point mass of a point mass is equal to the mass of the object times the square of the distance from the axis of rotation, or from the axis point. Okay, so all this right here is telling us basically the word version of our equation here. Okay, we're trying to find the moment of inertia of a specific point on that object. Okay. The units for moment of inertia are kilogram times meters squared. Okay, mass times radius squared would give us the obvious units of kilogram times meter squared, which means our mass always needs to be in kilograms. Our radius always has to be in meters. Okay. Objects have different formulas. That's what I was kind of talking to you about, depending upon the distribution of mass. So there's different distributions of mass, like compared to a bicycle tire or a weight of some kind, right? A bicycle tire, most of its mass is distributed along the outside, right? The wires or the metal that holds that wheel together doesn't weigh near as much as compared to the actual tire itself. Whereas like a weight would have even distribution of mass throughout the entire thing. Okay? We're going to use the basic formula, the I equals m times r squared, for things that have their mass distributed around that radius point, okay, around the edge of this exterior. And then we're going to look at the different moment of inertia equations in this table. Go ahead and turn to that. All right, so let's go ahead and read through it. Megan, can you read the problem for me? Uh-huh. Find out, is the moment of inertia greater when it's rotated around the middle or rotated around the end? Okay, so we kind of already gave a guess when we were talking about our pencil and what that feels like, but we'll see if we are correct. Okay, so let's go ahead and start writing down what we know here. All right, the length of our baton in total, so L, is equal to 0.65 meters. The mass of each of our objects here is going to be 0.3. Okay, so M equals 0.3 kilograms. Bless you. So what we're going to do is we're going to calculate the mass of each of those, or calculate the moment of inertia of each of those masses separately, so on both ends here. Okay, so you can follow along as we do that in your book. We're going to look at rotating the center of the rod first. So when we're holding our pencil like this first, we're going to calculate the moment of inertia on either end of that. And we're going to use our equation I equals m times r squared. Okay, of just looking at our single mass here. Okay. In order to do that, we've got to solve for the radius of this particular rod. Okay, so how do you solve from radius if we're given our entire length? Yeah, we just take it in half, okay? So in this particular one, R is going to be equal to 0.33, okay, or round it up to 0.33 meters. Okay, so when we're finding the moment of inertia of one of those masses on the end of this rod, we're going to take the mass, which is equal to 0.3 kilograms, times the radius, or the distance from the middle point to that mass, is 0.33 meters. and we square that. Okay, remember, because it's I equals m times r squared. All right, so that value gives us what? 0.033, and our units for moment of inertia are times meters squared. Kilograms times meters squared. Okay, so this is our moment of inertia for one of the masses. Okay, one of those masses on this baton. How do we find moment of inertia for the other one? Yeah, we do the exact same thing, right? The moment of inertia should be the same for the left side as it is for the right side, right? There's nothing different about that rod. So if we want to find moment of inertia of the entire object, all we need to do is take this by 2, right? If you look at your book, it says find the motion of the baton in itself. We're going to take I equals 2 times I of our single mass, okay? So all we're doing here, if we want to solve for moment of inertia of the entire baton, we're going to take 2 times 0.033, okay, and we get 0.066 kilogram meters squared. We have our one single thing that's rotating at this end, okay, where that single mass, that 0.3 kilogram mass is going to be rotating. We're going to use that same equation, except our radius is different because it's the entire length of the rod instead of just half of the rod. Okay, so we're still going to take our 0.3 kilogram mass times 0.65 meters squared. Okay, we're still using our I equals R times M squared equation. All right, and what value does that give us? 0.13 kilogram times meters squared. Okay, so for this one, we solved for this mass on the end of our baton, okay? One of the masses is our axis point, so it's not having any moment of inertia because it's the one that's in the center of the rotation. The moment of inertia only comes on this outside one because it has to resist. It wants to resist that change. So here, this moment of inertia that we solved for of this single mass that's on the end of our baton is going to be the moment of inertia of the total system, okay? So this is going to be our moment of inertia of our total baton, okay? Because there's only one of those ends that's rotating. Here we had 2 ends that were rotating, so we had 2 pieces that were resisting that rotation. Here we only have 1 end that's resisting the rotation. Okay, F equals m times a. So force is equal to mass times acceleration. We're going to be able to kind of connect these not only to angular momentum like we did, but we're going to connect them to the moment of inertia equations and problems. Okay, we're going to use this equation. Alpha equals net torque over moment of inertia. Okay, so alpha stands for what variable here?
Acceleration.
Angular acceleration. Okay. What we talked about torque last time. What does torque mean? Close. Torque tells us how effective a force is at making something rotate. Okay, so depending on where the force is applied and how big the force is, we're going to see how much rotation we get out of that. Okay, so torque kind of measures how effective it is, and then our moment of inertia here is telling us how much it's going to resist that change. Okay, how much the object's going to resist the change. So this is angular acceleration, torque over moment of inertia. Okay, what were our units then again for angular acceleration? Our units for angular acceleration?
Radians per second squared.
For alpha? Radians per radians per second squared. So for our alpha character, or for our angular acceleration, we should be radians per second squared. So this problem says a solid steel wheel with a mass of 15 kilograms and diameter of 0.44 meters. It starts at rest. we make it rotate at 8 revolutions per second in 15 seconds. So let's go ahead and just start making our list of what we have here. We have our mass, which is equal to 15 kilograms. We have our radius, which is equal to 0.22 meters. How did I get that 0.22 meters? Yeah, the diameter is 0.44, so I'm going to divide that by 2 to get my radius. This tells us the wheel starts at rest, and it gives us a revolutions per second angular velocity. Okay, our variable for angular velocity is what? What's the letter that goes with angular velocity?
Omega.
Yeah, omega, okay? So this means our initial omega is going to be 0 because it starts from rest, okay? And it ends up, so our final angular velocity is 8 revolutions per second. Do we want our angular velocity in revolutions per second? No. We want it in radians per second, okay? So the way we go from revolutions per second to radians per second is we make this T-chart that says 1 revolution equals how many radians? 2 pi, okay, right? 1 revolution is equal to 2 pi radians, entire circle. Okay, that way we're left with radians per second. All right, so we're going to take 8 times 2 pi, and we get what value for our angular velocity? Go ahead and put the pi into the equation. I don't want a pi in the answer. 50.3 radians per second. So here's my angular velocity, my final angular velocity, and the time that it took to do that was 15 seconds. Okay? So let's go ahead and start solving here. Our overall question right now for the first one says, what torque must be applied to the wheel? Okay? So we're going to solve first for torque. Can we do any of our really equations here without an angular acceleration, without an alpha? No, we can't. Okay? We don't have torque either. So we're going to go ahead and solve for alpha here, or angular acceleration. That equation, remember, is delta omega over delta t. Okay, or change in angular velocity over change in time. So we'll go ahead and solve for this right here. 50.3 minus 0, right, because that's what we started at, over 15 seconds. Okay. Which means our angular acceleration of this object is Evan, what'd you get? 3.35, so 3.4 radians per second squared. Okay? That's our alpha. Okay? If we look at our equation, alpha equals torque over moment of inertia, we're solving for torque right here. We have our alpha. We need to solve for moment of inertia now, okay, because that's our connection between the two. So if we look at this particular object, what moment of inertia equation should we be using? We're going to use our second moment of inertia equation off our table. So I equals 1/2 mr squared. Okay, so we're actually going to use this one to solve here for our moment of inertia, which is how much the object is going to resist that rotation. So I equals 1/2 times its mass, which is 15, times its radius squared. Its radius, remember, we found to be 0.22, and we'll square only that 0.22. Okay, the entire term does not get squared, only the radius gets squared. So make sure you kind of make a differentiation with that. Only the 0.22 gets the square here. So we get our moment of inertia to equal, what'd you get, Courtney? 10.9. 0.363 kilograms times meters squared. Once we have our moment of inertia, once we have our angular acceleration, we're going to plug back into this equation and solve for torque. Okay, so our angular acceleration should be 3.4 equals torque over 0.363. What'd you have?
1.233.
And what about our equations for torque? Or what about our units for torque, sorry?
It's a number.
Newton meters.
Newton meters. Newton meters. Okay. So that answers part A of our question. Part B says, if you apply a torque by wrapping a strap around the outside of the wheel, how much force should you exert? Okay, so what should the force be on this? So we have our torque. Let's think about what the equation for torque is.
Force times radius.
Force times radius, okay? Fr sine theta. Okay, Fr sine theta is our equation for torque. If you look at this picture, this force is being exerted kind of at basically on the x-axis, and our radius would be from the axis point to where that force is being exerted. So if you look at, I'm going to try and attempt to draw this. Oops. Maybe. Okay, if you look at this cylinder, the force is being applied in this direction right here. Okay, so if we kind of keep this force going right here, and we look at our radius, which goes from the axis point to the force itself, that's going to be at a perpendicular or at a 90-degree angle. Okay, so that means our theta here would be 90 degrees, which we know sine of theta to be, sine of 90 degrees to be 1. Okay, so we have our torque. We're going to find Fr sine theta. We're going to solve here for our force. So torque equals F times our radius, which we know to be 0.22, sine of 90 degrees, which we know is 1, and our torque value we solved for last time as being equal to 1.23. Okay, what'd you get for your force? 5.45. And what's our units for force? Newtons. Here, Brad's bicycle has a radius of 38 centimeters and is given an angular acceleration of 2.67 radians per second by applying a force of 0.35 newtons. What's the wheel's moment of inertia? So So here our radius was first given in centimeters. We can't have that.
0.38.
So we convert that to meters, which is equal to 0.38 meters. Okay, an angular acceleration. What variable does that go with? Alpha, good. And it's 2.67 radians per second. Our force that's applied is 0.35 newtons. And we're solving here for I. Okay. So what should be our process of trying to solve this? Okay. If we want to use our moment of inertia equation, we need to have mass. But do they give us mass? No. So we've got to go down an alternate route here.
So we can use our alpha, torque.
Exactly. We have to find torque first. So the equations that we have to solve for moment of inertia either are the ones listed on this sheet or it's this one. Okay, that's my little torque symbol. So that means we're going to have to solve for this because we can find torque given that we have a force and we have a radius. Okay, so let's go ahead and solve first for torque equals FR sine theta. If it doesn't tell you an angle that it's applied at, we assume it's being applied at a perpendicular, okay, or at a 90-degree angle, in which we just drop that sine theta because sine of 90 degrees is 1. Okay, so torque equals 0.35 times 0.38. Which means our torque is equal to what value? 0.133 Newton meters. Okay, do we agree up to that point?
Yes.
Okay. So now let's go ahead and plug in and solve alpha equals torque over moment of inertia. Alpha, they told us, was 2.67. Our torque was 0.133. And we're solving here for I, or moment of inertia. How do we solve for this I when it's on the bottom? We switch these two places, okay? So when our variable's on the bottom here and we need it switched, we're going to just switch this I and the 2.67. So then it will read I equals 0.133 divided by 2.67. That's what I got. And moment of inertia units?